The gold in your ring was born in a stellar explosion far more violent than anything on Earth. We are going to explore the 20 cataclysmic events that forge the universe's heaviest elements, revealing the dramatic origins of everything around you. By the end, you will understand the spectacular cosmic processes that crafted the very atoms making up your body and our world. How do colliding dead stars create precious metals, and what rare cosmic phenomena generate the uranium that powers our cities? What does it mean to know that we are all made from stardust? Our universe operates as the ultimate cosmic forge, its fires burning within the hearts of stars. This grand process is known as nucleosynthesis, the alchemy that builds the elements of our world from the simplest particles. It begins with the fusion of hydrogen into helium deep inside a star, a reaction that powers the star for millions or even billions of years. As a star ages and its core runs low on fuel, it begins fusing helium into carbon and carbon into oxygen, climbing step by step up the periodic table. Each new element forms from the ashes of the last, a chain of creation that builds ever heavier atoms. But this stellar cooking has a limit, a point where the cosmic kitchen cannot proceed with its usual recipes. That limit is iron. Fusing atoms together to make elements lighter than iron releases a tremendous amount of energy, which keeps the stars shining and stable. However, creating any element heavier than iron requires an input of energy instead of releasing it. For the star, this is a catastrophic turning point. Its core can no longer support itself through fusion, and the delicate balance between the outward push of energy and the inward crush of gravity shatters. This collapse triggers a spectacular death, a supernova explosion that floods space with neutrons. These free neutrons are captured by the collapsing star's material, rapidly building elements heavier than iron in a single, violent burst. But supernovae are not the only cosmic factories. Even more exotic events, like the collisions of unimaginably dense dead stars, provide the extreme conditions needed to cook up the universe's rarest treasures, from silver and gold to radioactive elements like uranium and plutonium. Every element on your periodic table, from the carbon in your cells to the calcium in your bones, has a dramatic origin story written in the fires of stars and the chaos of their endings. The life of a massive star ends not with a whimper, but with a cataclysm that reshapes its corner of the cosmos. After burning brightly for millions of years, such a star exhausts the nuclear fuel in its core. The outward pressure that has long fought a stalemate against gravity's relentless pull suddenly vanishes. In a single, breathtaking moment, the star's heart gives way, and the core collapses in on itself at nearly a quarter the speed of light. This is a core collapse supernova, the first of our great cosmic forges. The implosion is so violent and creates such immense pressure that it forges one last wave of new elements, primarily iron, nickel, and cobalt, in the star's final heartbeat. Then the collapsing core rebounds, sending a monumental shockwave racing back out through the star's layers. This wave blasts the entire stellar envelope, now rich with freshly minted heavy elements, out into the interstellar void. For a brief, spectacular period, this single explosion can outshine every star in its home galaxy combined. Within that expanding cloud of stellar debris, an even more exotic process often takes place. A flood of free neutrons released in the chaotic collapse bombards atomic nuclei. Atoms are forced to capture these neutrons incredibly quickly, a frantic race against radioactive decay known as the rapid neutron capture process, or the Are process. It is this R process that is responsible for creating some of the universe's most coveted treasures, including substantial amounts of gold and platinum. So the gold in a wedding band or the platinum in a catalytic converter was likely born in the violent death throes of a giant star, a stellar sacrifice that seeded the cosmos with the very materials that would one day form rocky planets and ultimately life itself. Yet some stellar explosions follow a different, even more predictable script. Picture a faint, Earth-sized cinder known as a white dwarf, the leftover core of a sun-like star. It is not alone, locked in a gravitational dance with a companion star. Over eons, the white dwarf's immense gravity pulls a stream of hydrogen and helium from its partner, slowly adding to its own mass. This theft continues in silence until the dwarf reaches a precise and critical threshold, a mass about 1.4 times that of our own sun. At that instant, the entire star is plunged into runaway nuclear fusion. The entire white dwarf ignites in a titanic thermonuclear blast, a Type 1, a supernova. This explosion is so uniform and so brilliant that it can outshine entire galaxies. Because these blasts always happen at the same mass limit, they always release nearly the same amount of light. This makes them perfect cosmic yardsticks, standard candles that astronomers use to measure vast distances across the universe and even discover its accelerating expansion. But their role as cosmic surveyors is only part of the story. In their ferocious heat, these supernovae forge immense quantities of iron and nickel, the very metals that make up a large part of our planet's core. They also flood space with other critical elements, like the silicon found in rocks and the calcium essential for our bones. This is a different kind of alchemy, born from a stellar partnership that ends in a predictable, universe-illuminating cataclysm. But there is a cosmic collision even more efficient at forging gold than a supernova. When two neutron stars, the unimaginably dense cores left behind by supernova, finally spiral into each other, they unleash a killer nova. This is a flash of light 1,000 times brighter than a typical nova, a brief but spectacular firestorm. In that cataclysm, immense clouds of neutron-rich material are ejected into space. Within these clouds, the conditions are perfect for the rapid neutron capture process, the same frantic R process that occurs in supernova, but here it operates on a far grander and more efficient scale. This single type of event is now thought to be the primary cosmic source for most of the universe's heaviest elements, including the gold in jewelry, the platinum in electronics, and even the radioactive uranium that fuels nuclear reactors. For decades, this was just a compelling theory. Then, in 2017, gravitational wave observatories felt the subtle ripples in space-time caused by such a collision. Traditional telescopes swiftly turned to that patch of sky, witnessing the brilliant kilonova firsthand. This was multi-messenger astronomy in action, confirming that these violent mergers are indeed the universe's ultimate heavy element factories. The very atoms of precious metals we unearth from the ground were likely born in such a spectacular, far-off collision, a direct link between the most extreme events in the cosmos and the elements that shape our civilization. The collapse of a massive star can forge an even more extreme crucible, a cosmic engine of staggering power. When a rapidly spinning giant star reaches the end of its life, its core does not just collapse into a neutron star. It falls completely inward, its immense mass crushing down into a newborn black hole. This is a collapsar, as vast amounts of stellar material swirl into the abyss, forming a superheated disk of matter. Powerful magnetic fields channel some of the infalling gas into two narrow, counter-rotating jets. These jets blast outward at nearly the speed of light, drilling straight through the outer layers of the dying star. If one of these ultra-focused beams is pointed directly at Earth, we witness it as a long gamma-ray burst, a flash of high-energy light so brilliant it can outshine 1,000,000 galaxies for a minute or two. These are among the most violent explosions since the Big Bang itself, but within that chaos lies a creative force. The environment around the newborn black hole, particularly in its swirling accretion disk and the bases of its jets, becomes a cauldron for the rapid neutron capture process. The intense temperatures and incredible densities provide a perfect, albeit fleeting, opportunity to forge some of the heaviest and rarest elements in nature. Scientists believe collapsars could be significant producers of elements like europium, used in the phosphors of television screens, and even radioactive thorium. This directly links the terrifying birth of a black hole to the creation of tangible matter, suggesting that some of the elements essential to our technology were born in the relativistic jets of these stellar monsters. The ongoing study of these incredible events continues to reveal that the pathways to creation in our universe are as varied as they are violent. The violence of a supernova does not always end with that initial brilliant flash. In the chaotic aftermath, as the stellar debris expands outward, a gravitational counter-current can pull a significant portion of that material right back toward the newborn remnant. This is the Supernova Fallback, a cosmic event where the explosion's own wreckage rains down upon the very thing it helped create. This returning material, rich with heavy elements from the blast itself, forms a superheated, incredibly dense accretion disk around the neutron star or black hole. It becomes a secondary, longer-lasting forge, where temperatures and pressures remain extreme enough to drive further nuclear reactions. Here, in this seething maelstrom of infalling matter, atoms can capture more neutrons, climbing even higher on the periodic table. This process is responsible for creating a distinct class of elements, including the strontium that gives fireworks their brilliant red color, and the barium used in medical imaging. The accretion disk around a newborn black hole is an especially potent crucible, its immense gravity and friction cooking the fallback material into some of the universe's heaviest substances. This reveals a profound truth about cosmic alchemy. The initial explosion is just the beginning. The real work of building a complex, element-rich universe often continues in the quieter, yet equally violent aftermath. The cosmos does not waste its own creative potential, finding ways to forge new matter even from the debris of its own most destructive events. Some stars are born with such immense mass that their final act defies even the spectacular drama of a typical supernova. We are talking about true stellar giants, behemoths hundreds of times more massive than our own sun. Deep within their cores, the temperatures soar so high that a bizarre and self-destructive process is triggered. The incredible thermal energy spontaneously creates pairs of particles and their antimatter counterparts. This sudden conversion of raw energy into matter, a process known as pair instability, robs the core of the very pressure holding it up. The star's central support system vanishes in an instant. The result is a pair instability supernova, a detonation of such staggering power that it completely obliterates the star, leaving no black hole or neutron star behind. Every single bit of the star is blasted into space in one of the most energetic events since the Big Bang. These cosmic firestorms forge and scatter immense quantities of newly minted elements. They are prolific producers of oxygen, the very air we breathe, silicon for the rocks beneath our feet, and vast amounts of iron. In the early universe, before many generations of stars had lived and died, these titanic explosions were likely the primary source of the first heavy elements, seeding infant galaxies with the raw materials for everything to come. Their sheer power influences how a galaxy evolves, churning its gas and enriching it with a specific chemical signature. The existence of such stars reveals a fundamental limit to stellar life, a point where a star becomes so massive that it is fundamentally unstable, destined to vanish in a final, universe-shaping flash of creative destruction. Not every star dies in a blaze of cosmic violence. Some of the universe's most vital elements are forged in a far more gentle, prolonged exhale. Consider a star like our own Sun, but in its final chapter. It has exhausted the hydrogen in its core and swelled into a vast, luminous red giant, entering a phase known as the asymptotic giant branch. Here, the star becomes deeply unstable, its outer layers churning like a pot coming to a slow, rolling boil. This turmoil generates powerful stellar winds that steadily blow the star's own atmosphere out into the void. This is not a sudden explosion, but a continuous, drifting loss of material, a cosmic breeze that carries away the star's inner secrets. Within those expelled gases are incredible riches. The star's interior has become a layered furnace. In one shell, helium fuses into carbon. In another, hydrogen fusion produces helium, along with a generous supply of nitrogen. These newly minted elements are dredged up to the surface by powerful convection currents, and then gently carried away by the stellar wind, enriching the surrounding space with the fundamental building blocks of life. But the true alchemy happens even deeper. In the star's heart, temperatures are just right for a different kind of element building, the slow neutron capture process, or S process. Unlike the frantic R process of supernova, this is a leisurely, methodical climb up the periodic table. Atomic nuclei slowly absorb neutrons, one at a time, waiting patiently for a neutron to radioactively decay into a proton before capturing the next. This gradual stepping stone approach builds a specific class of heavy elements, including the technetium used in medical imaging and the zirconium that forms the brilliant gems in many pieces of jewelry. This peaceful expulsion demonstrates a profound truth about our galaxy's evolution. Cataclysmic events are not the only source of cosmic wealth. The quiet, persistent winds from these aging stars provide a steady, reliable drizzle of newly forged elements, a gentle enrichment that has, over billions of years, filled the interstellar medium with the diverse chemistry necessary for planets and ultimately for us. While the gentle winds of red giants provide a steady enrichment, the most massive stars unleash a far more ferocious gale. Wolf-Rayet stars are stellar monsters, the exposed, blazing cores of stars that were once far larger than our Sun. These titans have shed their outer hydrogen envelopes through winds of such unimaginable force that they are literally blowing themselves apart. The result is a star stripped bare, shining with the intense, ultraviolet glare of its helium and nitrogen-rich core. This is not a gentle breeze but a hurricane of stellar material, with winds racing outward at millions of kilometers per hour. These powerful outflows are more than just destruction, they are prolific cosmic factories. The exposed core, burning at ferocious temperatures, forges immense quantities of carbon and oxygen. These newly created elements do not wait for a final explosion. They are immediately caught up in the stellar hurricane and blasted directly into interstellar space. A single Wolf-Rayet star can eject more than the mass of our entire Sun in this way over just 100,000 years, seeding its surroundings with the raw materials for future stars and planets. These winds do not just carry elements, they can also trigger their creation. As the high-velocity wind rams into slower-moving gas that the star shed earlier in its life, it creates immense shockwaves. The heat and pressure within these collisions can become intense enough to jump-start nucleosynthesis in the surrounding material, forging even more heavy elements right in the star's own backyard. This continuous pre-supernova enrichment profoundly influences the chemical makeup of entire galactic neighborhoods. By studying these stellar powerhouses, astronomers gain a crucial window into the final, volatile chapters of a massive star's life. They reveal how the universe begins dispersing the ingredients for complex chemistry long before the star's final, cataclysmic supernova, ensuring that the legacy of these giants is woven into the fabric of new solar systems. Even the quietest cinders in the cosmos can flare into life given the right partner. A white dwarf, the Earth-sized remnant of a star like our Sun, can become a periodic cosmic forger if it orbits close to another star. Its intense gravity steadily steals a thin stream of hydrogen gas from its companion. This stolen material does not simply accumulate. It spirals down onto the white dwarf's incredibly dense surface, piling up layer by layer until the pressure and heat at the base of this hydrogen ocean become unbearable. Then, in a brilliant flash, the entire accumulated layer ignites in a runaway thermonuclear explosion. This is a nova, a stellar outburst that can make a faint, dead star shine tens of thousands of times brighter for a few fleeting days. While far less energetic than the supernova that destroys its stellar cousin, a nova is a potent crucible in its own right. The ferocious heat of the surface blast fuses the stolen hydrogen into a fresh wave of heavier elements, including vital amounts of carbon, nitrogen, and oxygen. These are the fundamental elements of life, forged in a flash on the surface of a dead star and then blasted out into space by the force of the explosion. Perhaps even more surprisingly, these events are now understood to be a primary cosmic source for a specific, lightweight element, lithium. This metal, essential for the batteries in our phones and laptops, is notoriously fragile and easily destroyed in the interiors of larger stars. Yet nova create and eject it in significant quantities, contributing to the galactic supply of this crucial resource. This cycle of theft and explosion can repeat itself every few thousand or even 100 years as the white dwarf begins siphoning fuel all over again. This reveals a different rhythm to cosmic enrichment. It is not always about singular, universe-shattering cataclysms. The persistent, cyclical fireworks of nova provide a steady, recurring drizzle of newly forged elements into the galaxy, a testament to how even smaller, repeated events can, over cosmic time, profoundly shape the chemical landscape of the universe. The surface of a neutron star is a place of unimaginable extremes where a teaspoon of matter would weigh billions of tons. When such a star orbits a stellar companion, its crushing gravity can pull a stream of gas onto its surface. This infalling hydrogen and helium does not land gently. It piles up into an ocean of fuel, compressed and heated by the star's immense gravity, until the entire layer erupts in a thermonuclear firestorm. We see this from Earth as a brilliant, fleeting X-ray burst, a flash of high-energy light that can outshine our Sun 100,000 times over in mere seconds. This is not a slow burn, but a runaway explosion racing across the stellar surface. Within that inferno, a frantic nuclear process unfolds, the rapid proton capture process. Unlike the neutron capture of supernova, this RP process forces atomic nuclei to grab protons one after another, climbing the periodic table at a breathtaking pace before the nuclei have a chance to radioactively decay. In these few seconds of stellar violence, the burst forges a unique suite of elements, including isotopes of strontium, the element that gives emergency flares their deep red glow, yttrium used in laser systems, and zirconium, the very substance of cubic zirconia gems. The intense magnetic fields of the neutron star channel the blast, creating conditions so alien they cannot be replicated in any laboratory on Earth. These bursts are, in essence, natural experiments in extreme physics, revealing the pathways by which atomic nuclei are built under the most severe gravitational and thermal stress. Each flash is a miniature cosmic forge, demonstrating once again how the persistent pull of a dead star upon a living one can, in a violent instant, contribute to the galaxy's rich chemical diversity. The fury of a star's death can ignite creation in its own backyard. We have seen how a supernova blast scatters new elements into the void, but the story does not always end at the shockwave's edge. Sometimes the star had already cast off vast shells of its own atmosphere in the centuries before its final cataclysm, when the supernova's immense shockwave, traveling at a fraction of the speed of light, slams into this pre-existing circumstellar material. A secondary cosmic forge roars to life. This is not the primary explosion itself, but a powerful echo of its creative power. The collision is unimaginably violent, compressing and heating the ejected gas to incredible temperatures. Within this superheated interface, nuclear reactions are triggered anew. The circumstellar material, already rich with elements like oxygen and silicon, is cooked into even heavier substances. This secondary nucleosynthesis is a prolific source of certain isotopes, particularly titanium, the metal that makes modern jet engines strong and lightweight, and chromium, the element that gives emeralds their green glow and protects our cars from rust. The radiation from this violent interaction glows across the entire electromagnetic spectrum, from radio waves to gamma rays. To an astronomer, this brilliant afterglow is more than just a light show, it is a detailed history book. The specific elements we detect and the intensity of the light reveal the composition of the material the star shed in its final years, telling a story of its unstable late stages long after the star itself is gone. This interaction forces us to see a supernova not as a single, isolated detonation, but as a complex, multi-stage event. The star's own past, written in the winds it blew into space, directly shapes the final chemical legacy of its death. The universe weaves its elements through a tapestry of cause and effect, where even the debris of a star's life becomes the raw material for its final, spectacular act of creation. Even black holes, the universe's ultimate consumers, can become unlikely creators. Far from being simple voids, a feeding black hole is a place of immense constructive potential. As matter spirals inward, pulled by the black hole's irresistible gravity, it does not fall straight in. Instead, it forms a whirling, superheated structure known as an accretion disk, a cosmic whirlpool of gas and dust that glows with the heat of a billion stars. Within this maelstrom, temperatures and densities reach such staggering extremes that nuclear fusion is not only possible, it is inevitable. The frantic collisions between atoms in this high-energy environment can forge a whole new suite of elements, from carbon and oxygen all the way up to iron. But the true mystery lies in what happens beyond that familiar limit. The unique, relativistic conditions near the event horizon might allow for processes we cannot yet replicate or even fully model. Theorists suggest that novel forms of nucleosynthesis could occur here, pathways that build elements we rarely see elsewhere in the cosmos. This transforms our understanding of a black hole's role in the galaxy. It is not merely a gravitational sinkhole that removes matter from the universe. Under the right conditions, it can act as a powerful engine of chemical enrichment, taking in raw material and expelling newly forged, heavier atoms through powerful jets and outflows. This revelation challenges a fundamental assumption, forcing us to see these mysterious objects as dynamic participants in the cosmic cycle of creation and destruction. The very engines of oblivion might also be secret workshops, quietly contributing to the complex chemistry that makes worlds like ours possible. A star's final journey can sometimes lead it directly into the maw of a monster. When a sun-like star wanders too close to the supermassive black hole at the heart of its galaxy, it meets a uniquely dramatic fate. The black hole's immense gravity pulls more strongly on the side of the star facing it than on the far side, stretching the star horizontally while compressing it vertically. This difference in gravitational pull, known as a tidal force, overcomes the star's own gravity and shreds it into a long, thin stream of incandescent gas. This is a tidal disruption event, a cosmic demolition that unfolds over just a few hours. About half of the stellar debris is flung out into the darkness of intergalactic space, while the rest forms a vast, swirling accretion disk around the black hole. As this material spirals inward, it is compressed and heated to temperatures of millions of degrees, creating a temporary, brilliant flare that can outshine every star in its galaxy for months. Within this superheated disk, conditions become ripe for nucleosynthesis. The frantic collisions of atomic nuclei in this high-energy environment can forge new, heavier elements, adding to the chemical diversity of the galactic core. While far rarer than supernova, these events are crucial for understanding the chemical evolution of galaxies, particularly their dense central regions. They demonstrate that the simple gravitational dance between a star and a black hole can, for a fleeting moment, ignite a potent cosmic forge. This ephemeral alchemy directly links the most powerful gravitational engines in the universe to the creation of the raw materials that may one day form new worlds, revealing yet another surprising pathway for element building in the cosmos. Long before the first galaxies took shape, the cosmos was a simpler, far emptier place. It was filled with nothing but the pristine, primordial elements of hydrogen, helium, and a trace of lithium, forged in the fires of the Big Bang itself. Into this silent darkness, the very first stars ignited, colossal giants known as population 3 stars. They were unlike any sun we see today, composed purely of those light elements, free from the contaminating dust of heavier metals. This purity allowed them to grow to staggering sizes, hundreds of times the mass of our sun, burning with a ferocious, ultraviolet intensity that began to illuminate the cosmic dark ages. Their lives were brilliant but incredibly brief. A star of such immense mass consumes its nuclear fuel in only a few million years, a mere heartbeat in cosmic time. Their deaths were as unique as their birth, culminating in supernova of unimaginable power. These were the universe's very first heavy element factories. Within their cataclysmic final moments, the first atoms of carbon, oxygen, and iron were forged from nothing but hydrogen and helium, the initial steps in a chemical chain reaction that would eventually lead to us. The nucleosynthesis within these primordial stars was fundamentally different from what occurs today. Without any pre-existing heavier elements to act as catalysts or to be reprocessed, their internal fusion pathways created a distinct chemical signature. They produced a far greater ratio of certain elements like oxygen compared to iron, a pattern that would become imprinted on the next generation of stars that formed from their ashes. By studying the oldest, most metal-poor stars in our own galaxy, which are the direct descendants of that first enriched gas, astronomers can read this ancient chemical fingerprint. This allows them to reverse engineer the properties and the dramatic deaths of those first stellar pioneers. Understanding these events is like finding the first chapter of a long-lost cosmic history book. It reveals the initial conditions for all element formation, setting the chemical trajectory for every star, planet, and life form that would follow in the billions of years to come. The very existence of our complex, element-rich world is a direct legacy of those first universe-shaping cataclysms at the dawn of time. Magnetism itself can become a cosmic force of creation. Beyond the immense gravity and blistering temperatures of stellar events, there exists another, more subtle architect of matter, the magnetic field. On the surface of a special class of neutron stars known as magnetars, these fields reach almost unimaginable strength. A magnetar's magnetic field is a quadrillion times more powerful than the one shielding our own planet. Occasionally, the colossal stress of this field, tangled and strained by the star's own rapid spin, becomes too much to bear. The crust of the neutron star suddenly cracks, releasing a cataclysmic burst of energy, a Magnetar Flare. For a fraction of a second, this single event can outshine every star in our entire galaxy. The flare unleashes a firestorm of gamma rays and a torrent of high-energy particles, bathing the space around the star in a tempest of radiation. This radiation is so intense it can fundamentally alter the atoms it touches, stripping them apart and forcing their nuclei to reassemble in new, exotic configurations. This violent environment can trigger a unique form of nucleosynthesis, forging rare heavy elements that might not form easily in other cosmic explosions. The magnetic field itself does more than just provide the energy for the flare. It actively guides the nuclear reactions that follow. The field lines act like invisible tracks, channeling charged particles and influencing how atomic nuclei capture neutrons, potentially leading to the creation of isotopes with distinct and unusual signatures. This reveals a profound layer of complexity in the universe's recipe for matter. It is not just about heat and pressure. The invisible architecture of magnetic fields can directly sculpt the very atoms that emerge from a stellar cataclysm. The legacy of a magnetar, therefore, might be written in the subtle, unique chemical fingerprints of elements scattered across the galaxy, a permanent record of the most powerful magnetic forces in existence. But the cosmos does not build only through immense acts of fusion. Sometimes creation arrives through a shattering. Racing through the emptiness between stars are cosmic rays, atomic nuclei accelerated to nearly the speed of light by the shockwaves of ancient supernova. These are not gentle messengers, they are high-energy bullets, and when one slams into a heavier, slower-moving atom drifting in the interstellar medium, the result is a violent fragmentation. This process is known as cosmic ray spallation. Imagine a heavy, intricate ceramic vase struck by a hammer. It does not fuse into something new, it shatters into a spray of fragments. In this cosmic demolition, a nucleus of carbon or oxygen, for instance, is broken apart by the impact. From its pieces, a different class of elements is born. This is the primary source for most of the universe's lightweight elements like lithium, the key to our modern batteries, beryllium, used in specialized alloys and telescopes, and boron, an essential nutrient for plants. These are elements too fragile to survive the infernos inside most stars, and too light to be built in any significant quantity by the Are process. Their existence relies entirely on this destructive act happening in the cold, dark vastness of interstellar space. This reveals a beautiful duality in cosmic chemistry. The same supernova shockwaves that forge gold in their hearts also accelerate the cosmic rays that, millions of years later, will shatter other atoms to create lithium. It is a cycle where destruction and creation are two sides of the same coin, a continuous interplay that fills the galaxy with the full spectrum of elements, from the lightest to the very heaviest. The brilliant heart of a distant galaxy can sculpt its own future. Far beyond the realm of individual stars, the supermassive black holes that power quasars unleash energy on a truly galactic scale. As these cosmic engines devour surrounding matter, they do not consume everything. Some of the infalling gas is redirected by intense magnetic fields and radiation pressure into colossal, high-speed outflows. These are not gentle breezes, but hurricanes of matter racing away from the galactic center at thousands of kilometers per second. When these supersonic winds slam into the cooler, denser gas clouds floating in the galaxy's halo, they create immense shock fronts, cosmic tsunamis of unimaginable force. Within these turbulent, superheated interfaces, the conditions become perfect for nucleosynthesis. The violent compression and intense radiation can trigger nuclear reactions in the interstellar gas, forging new generations of heavy elements like oxygen, neon, and sulfur right in the galactic outskirts. This process does not just enrich the host galaxy, it fundamentally changes its environment. The quasar-driven winds carry these newly forged elements far beyond the galactic disk, polluting the vast and seemingly empty intergalactic medium with the seeds of future chemistry. This reveals a profound connection between the growth of the largest black holes and the chemical evolution of the entire cosmos. The most luminous objects in the universe are not just passive beacons, they are active participants in a grand cycle. They take in raw material and, through their incredible power, help process and distribute the very elements that will one day form new stars, planets, and perhaps even life across entire galaxy clusters. The legacy of a quasar is written not only in the light we see, but in the enriched chemical tapestry it weaves throughout the fabric of space itself. But the most elusive ingredient in the cosmos might also be a hidden forger. Invisible dark matter outweighs all the stars and galaxies we can see, its gravitational pull sculpting the universe on the largest scales. While its true nature remains one of science's greatest mysteries, some compelling theories suggest it could play a direct role in the cosmic creation of elements. The idea centers on what happens when dark matter particles meet. In regions where dark matter is exceptionally dense, like the cores of galaxies or within massive stars, these particles could collide and annihilate each other. This annihilation would be a conversion of pure shadow into tangible substance, transforming into a burst of standard model particles, including protons, neutrons, and their antimatter counterparts. This sudden injection of fundamental building blocks could, in theory, provide the raw materials for nucleosynthesis. It might offer a novel pathway to build heavier elements in environments where traditional fusion has ceased. The implications are staggering. It suggests that the very fabric of the invisible universe could be subtly enriching the visible one, contributing to the chemical diversity we observe in ways our current models do not account for. This hypothesis sits at the thrilling intersection of astrophysics and particle physics, a frontier where our understanding of the very small meets the mysteries of the immensely large. While still speculative, this possibility reminds us that the story of cosmic alchemy is far from complete. The universe's heaviest elements may not just be born from the light of dying stars, but also from the silent, unseen interactions of the dark cosmos itself. Even the most tranquil stellar death can be a profound act of cosmic generosity. After a star like our Sun spends its final millennia as a red giant, it does not explode. Instead, it gently exhales its own atmosphere into space, creating one of the most beautiful structures in the universe, a planetary nebula. These glowing, intricate shells of gas are not the aftermath of violence, but the carefully shed outer layers of a dying star, illuminated by the intense ultraviolet light from the hot core left behind. This process is slow and elegant, a cosmic bloom that unfolds over thousands of years. Within these expanding, luminous clouds lies a rich chemical legacy. The gas is not just simple hydrogen and helium. It is a complex soup of elements forged during the star's long life. The star's interior has dredged up vast quantities of carbon, the fundamental building block of life, and nitrogen, a crucial component of our atmosphere and DNA. This is the star's final gift to the galaxy, a gentle dispersal of the very ingredients needed for biology. But the contribution goes even deeper. For many of these stars, the same slow neutron capture process that operated in their final stages has also produced a suite of heavier elements, the S-process elements. This includes substances like technetium and zirconium, which are now carried outward on the stellar breeze. The formation of a planetary nebula is therefore a critical recycling mechanism. It demonstrates that cataclysmic force is not a prerequisite for cosmic enrichment. These serene, picturesque events provide a steady, reliable method of dispersing newly forged elements, ensuring that the interstellar medium is continually seeded with a diverse chemical palette. The eventual death of our own sun will follow this same quiet, beautiful script. It will not go out in a supernova blaze, but will instead weave its own contribution into the galactic tapestry. Its expelled gases destined to one day become part of new stars, new planets, and perhaps new life. This gentle exit underscores a fundamental truth about the cosmos, that every star, regardless of its size or final fate, plays an essential role in the grand, continuous cycle of matter. The fading echo of a gamma-ray burst holds secrets just as profound as its initial flash of light. Long after the primary beam of radiation has vanished, its afterglow lingers for days or even weeks, a persistent ember in the distant cosmos. This sustained emission is not merely a dying echo, it is an ongoing cosmic event in its own right. The initial explosion propels material outward at relativistic speeds, and this ejector eventually slams into the surrounding interstellar medium, creating powerful, long-lasting shock waves. Within these turbulent fronts, temperatures and pressures remain extraordinarily high, creating a secondary forge in the burst's wake. Here, nucleosynthesis continues, with atomic nuclei bombarded by particles in the chaotic environment, potentially building a unique suite of heavy elements. The specific chemical signature of this prolonged creation is different from what is made in the initial cataclysm. By carefully analyzing the spectrum of this fading light, astronomers can detect the fingerprints of newly forged elements, directly measuring the chemical yield of one of the universe's most energetic phenomena. This transforms our understanding of these brief, brilliant flashes. They are not just instantaneous detonations, but the igniting spark for a longer, more complex process of chemical enrichment. The most valuable data often comes not from the main event, but from the detailed forensic analysis of its aftermath. This patient observation reveals that the universe often continues its work of creation quietly, in the lingering light of its most violent outbursts, weaving complexity long after the initial drama has faded from view. Each of these 20 cosmic forges adds its own unique thread to the universe's grand chemical tapestry. The gentle winds of an old star gift us the carbon for life, while the violent merger of dead stars hammers together the gold for a crown. A supernova seeds space with iron for a planet's core, and a Magnetar's flare might forge a rare element found nowhere else. No single event could have created the full richness of the periodic table we see today. It is the combination of all of them, operating over billions of years, that has filled the cosmos with the chemical diversity necessary for planets, oceans, and life. Our ability to read this story is a triumph of modern science. Gravitational wave observatories feel the ripples from colliding neutron stars, while space telescopes like the James Webb peer back to the era of the first stars, analyzing the light of infant galaxies to decode their elemental composition. Each new instrument is like a new chapter in a detective story, revealing with greater clarity how the universe built itself from simplicity into complexity. This knowledge transforms our perspective on existence. The calcium in your bones was forged in a long-dead star. The oxygen you breathe was expelled by a red giant. The iron in your blood that carries that oxygen was born in a stellar explosion that occurred before our sun even ignited. We are not just living in the universe, we are a temporary assemblage of its most ancient and epic creations. This understanding of our cosmic origin is one of the most profound gifts of astronomy, connecting our own story directly to the grand narrative of the cosmos itself. Our journey through 20 cosmic forges reveals a universe of breathtaking creativity and violence. We have witnessed how supernovas scatter iron across the void, how colliding neutron stars hammer together gold, and how the gentle winds of dying stars gift us the carbon of life. Each cataclysmic event plays its unique and vital role in the endless cycle of matter, a grand cosmic rhythm of birth, death, and rebirth that has been unfolding for billions of years. This knowledge forges a profound connection between the vast cosmos and our own existence. The calcium in your bones, the oxygen in your lungs, the iron in your blood, every single atom in your body beyond the most basic hydrogen was forged in one of these spectacular stellar phenomena. We are not merely inhabitants of the universe, we are its living legacy, a temporary assemblage of stardust given consciousness. As our telescopes peer deeper into space and our detectors listen more closely to the subtle ripples in space-time, new discoveries will undoubtedly reveal even more exotic forges and expand our understanding of this cosmic alchemy. This story is still being written. Thank you for exploring these origins with us. If this journey into the heart of creation resonated with you, please like this video, subscribe for more cosmic explorations, and share your own thoughts and questions in the comments below. Never stop looking up at the night sky, for in its silent, glittering depths lie the secrets of our own beginning.